Hello friends, welcome to a new tutorial in wave propagation. In today's interesting tutorial, we'll talk about tropospheric propagation. We know that the atmosphere adjacent to the Earth is known as troposphere and ground wave propagation happens there. But how is ground wave propagation different from tropospheric propagation? We'll see in this video. If this is something that interests you, then please keep watching. By definition, the tropospheric region is the atmosphere adjacent to the Earth extending up to 16 kilometers, and the wave propagation beyond line of sight is possible using this mode of propagation. So that's the first key point of difference of tropospheric propagation from that of ground wave propagation. We know that ground wave propagation is only possible for line of sight communication. So when we want to go beyond line of sight communication, we'll take help of tropospheric propagation, and we'll see that in a minute. Now, several different mechanisms and phenomena are responsible for tropospheric propagation. I need to specifically mention these phenomena because of which is a different kind of propagation has evolved, and these phenomena are listed here. Diffraction is already known to you, that whenever a wave hits a solid body in the atmosphere, it is subjected to change its path, which is known as diffraction. And then we have the normal refraction, which is the cause of the gradual bending of the wave as we send the wave upwards. But these two parameters or these two mechanisms are unique to tropospheric propagation, which are abnormal reflection and refraction and tropospheric scatter. So we'll talk about these two in detail, and then we'll get to know how tropospheric propagation has originated. Before we diverge into the discussion of tropospheric propagation, we need to understand the difference between a standard atmosphere and a non-standard atmosphere. Please understand, a standard atmosphere is something where the temperature decreases at the rate of 6.5 degrees per kilometer. So as we move up, the temperature decreases and it reaches minus 50 degrees at the upper boundary of the atmosphere of the Earth. But a non-standard atmosphere is defined by irregularities. We know that the dielectric constant near the surface of the Earth is almost equivalent to 1, and the presence of water vapor increases, the dielectric constant also increases. So you could note this point down, that the presence of water vapor increases the dielectric constant, and the presence of water vapor is irregular at irregular periods of the year. So that brings us to the phenomena of abnormal reflection and refraction. And some effects due to the non-standard atmosphere conditions are super refraction, sub-refraction, duct propagation, and tropospheric scatter. That is what are the classification of phenomena which falls under the category of tropospheric propagation. So let's see those one by one. Now this is super refraction phenomena. The transmitter is located at a hot terrain and the receiver is located at a lower temperature terrain or a colder region. Then the path of the wave is something like this, and this is known as super refraction. This refraction is unusual. This is a lot larger than what is expected out of the normal sending of the wave. And then exactly the opposite of that happens when the transmitter is located at a colder terrain and we want to send the signal towards warmer areas. The refracted path moves in the upward direction abnormally, and this is known as sub-refraction phenomena. So these two phenomena, they must be understood, that whenever we send the wave from warmer terrain to colder terrain, it encounters super refraction, and when we send it from colder terrain to hotter terrain, it follows sub refraction phenomena. Then we need to understand the duct propagation. In order to understand duct propagation, we need to see that to understand duct propagation, we need to understand a phenomena known as excess modified refractive index, denoted by M. And if you look at M, it depends upon eta and height and the radius of the earth. And we know that eta depends upon the concentration of water vapors, as we discussed previously. So the irregularities in eta will cause irregularities in M. And if we plot a graph between M, which is excess modified refractive index, so it is different from N. So this M will take into account the irregularities of the troposphere because of the presence of the water vapors. And a standard atmosphere should look something like this. It should have a linear graph where M increases linearly as the height increases, but that does not happen in ideal case. If M decreases with the increase of height for certain height, and then it starts to behave like standard atmosphere, then a duct is created here within this height, and this duct is known as the ground duct or the surface duct. And there could be some regions where the atmosphere could behave like a standard atmosphere up to some height, let us say H1, and then it will start to invert up to H2, and then it will start to behave like standard atmosphere again. And in this case, the area of inversion will lie well above the ground, and it is known as elevated duct. And when the wave enters into any of these ducts, it encounters reflection like this. So this is an example of surface duct or ground duct. The wave is being reflected, and now this is an example of elevated duct where the wave is reflected in the elevated duct which is lying well above the ground at certain height, or the subsequent bouncing of the wave in the duct. So it can cross a region well beyond the line of sight propagation. Then finally we have the concept of tropospheric scatter. Then we have tropospheric scatter. Please understand, tropospheric scatters are related to atmospheric blobs or turbulences. Due to some irregular activities in the atmosphere, there could be a blob which is created in the atmosphere which looks something like this. It looks like a cloudy thing. It's actually a blob. It's a scatter volume. And any wave which is incident at this scatter volume stays here. The wave scatters in this region and is available to be caught by any receiver. If the receiver is receiving the signal from this scatter volume, it will receive all the signal which was transmitted to this scatter volume. So scatter volume could be thought of as a buffer space which is created in the troposphere because of the irregular atmospheric conditions or turbulences. Now there are few key points in tropospheric scattering like back scatter, forward scatter and side scatter. And then we have scatter volume and scatter angle. We can see all those points being discussed here in this diagram. The forward scatter refers to the incident wave from the receiver antenna. The receiver is directed towards this scatter volume to receive the signal. So this becomes the forward scatter, and you can see this becomes the loss scatter. the incident portion of the receiving antenna that goes beyond this scatter volume is the loss scatter. So anything which is caught from the scatter volume is meaningful, and the angle which is made between these transmitting wave and the receiving wave is known as the scatter angle, and they should meet at the scatter volume. Both transmitter and receiver, they should be oriented in such a way that they should intersect at maximum area in the scatter volume. So that's how tropospheric scattering has different phenomena like duct propagation and scatter volumes, and then we have super refraction and sub refraction. So these are the phenomena which make tropospheric propagation different from ground wave propagation. This is mostly a theoretical topic, and in the exam also you'll be asked to define these phenomena. So I hope this quick tutorial was of help. If you liked the video, give it a thumbs up. Consider subscribing to the channel. I'll see you around in the next video. Take care. Bye bye.